Okay, our essential question in this video is, what if a solution has the square root of a negative number? What if a solution has the square root of a negative number? So, I don't know if we've run into this yet in class. If we haven't, we eventually will. But there will be times when you find the solution of a quadratic and you end up with a square root that has a negative number in it. And we cannot solve that. There is no number multiplied by itself that gives you a negative number. We know that every time you square a number, whether it's positive or negative, it changes it to positive. So, mathematicians have come up with a way to solve these equations anyway. And they have come up with this idea of an imaginary number. So I know it sounds kind of strange, but we're going to talk about imaginary numbers and see how they play into this section, how we can use them to write our final answers when this particular situation comes up, when we have a square root of a negative number. Alright, so let's take a look at this imaginary number, and we represent imaginary numbers with the letter I, and it's in cursive. So you're going to make a little, when you draw it, you're going to do it like this. I'll show you. It's going to be like a little reflected J. So that instead of going to the left with our little curve, we're going to go to our right. So I. And I represents the square root of negative 1. And you're going to see how we use this now to write our solutions when we have this kind of situation show up, a square root of a negative number. Now, one other thing I want you guys to notice is, you remember this, if you have a square root and you square it, a square root and a square, they cancel each other out. They undo each other, just like a multiplication and division. You take a number, divide by 2, and then multiply it by 2, you get the same number back again. You take a number with addition and subtraction, same thing. Take a number and add 5, and then you subtract 5, you go back to your original number. Well, square and square root undo each other as well. So an interesting property of I is when you square I, it actually means the square root of negative 1 and the whole thing squared. And since we know that a square root and a square cancel each other, the square root goes away and the square goes away, and we end up, hang on a second while I get my computer to catch up with me here, we end up with just negative 1. So whenever you see I squared show up in your solution, you can just change that to negative 1, since that's the square root of 1 squared. Okay, let's take a look at this final part before we work on some things. What's a complex number then? So a complex number is going to look like this. You're going to have two parts for a complex number. Let's make an example of one. 9 plus 3i. 9 plus 3i. Let's get rid of that little mark. And for a complex number, here's what we say. This part right here, the first term, this 9, this is the real part. That's a real number. I don't know why my computer is delaying a little bit. Sorry about that. That's the real part of the complex number. And then the 3 times I, well, I is imaginary. So 3 times I, that is the imaginary part. Now, technically, class, we could write every number as a complex number. Just an example, or I'll write this down and show you this. If I want to write the number 5, I could just write 5 plus 0i. Well, 0 times I is 0, and that just changed to 5. The imaginary part goes away, and the 5 stays there. So even regular numbers, we can write them as complex numbers. All we add is 0 times I. We could also say this number right here, so negative 4i, that's the imaginary part. If we want to write that as a complex number, we just add the real part to it and just say that part is 0. So 0 minus 4i is just pure imaginary, but we can write it as a complex number. So you can use 0 to play with that a little bit and write everything as a complex number. So there's an imaginary number. I is the square root of -1. There's the complex numbers. Now let's talk about how to add and subtract complex numbers. The cool part is it's exactly the same thing as adding and subtracting polynomials like we have done before. So let's take an example here. I'm gonna draw a line down the middle of this page because we're gonna do two examples here. Let's see if I can get that to be straight. That's good enough. So let's fix that a little bit. So I'm going to do the thing that we've done before. We're going to go ahead and add two binomials together, just regular binomials. So let's write this out. I'm going to write 9 plus 5x, and we're going to add that to 6. And I apologize again, my computer is doing all kinds of things in the background. I'm not sure what it is, but everything I'm writing is just delayed where it's messing me up. Let's try this again. This is going to be 6 minus, and we'll put 2x. Now, normally the x term is going to be in the front, but it doesn't have to be. Let's go ahead and go through our normal procedure for adding polynomials. We're going to group like terms. So I'm going to go ahead and do this in the vertical method. So I'm going to go ahead and say, okay, I've got a 5x here. That's a positive 5x. And then I've got a positive 9 over here. And then this adding a polynomial means the signs all stay the same. That's a positive 6. That will go here. And then I've got a negative 2x. That's going to go here. So with the vertical method, we've got 5x minus 2x. That's 3x. And 9 plus 6 is 15, and that's going to be positive. And now we have our new binomial, which is the sum of the two binomials above. And just notice, class, I want the x term in front because I've taught you guys before that we always want to put our final answer in standard form. So we're going to go from highest exponent to lowest exponent, and then we're going to end with a constant if we have one. Alright, now what does this look like when we're adding and subtracting imaginary or complex numbers? Let's write these same numbers now, except for now, instead of putting an x there, we're going to put an I there. So 9 plus 5i, there's an imaginary or a complex number. And then we'll put in here 6 minus 2i. Okay, well, let's look at this. The solution is going to be identical. We're going to group our like terms together. So here we've got a 9. Actually, let's do the i's first. We've got a 5i, and we've got a negative 2i over here because the plus sign means our signs stay the same. We've got negative 2i, and then over here we've got a 9. And we've got a positive 6. So now we're going to get 5i minus 2i. We can subtract it the exact same way that we would subtract a coefficient with a like variable. This is just 3i. And then 9 plus 6 is 15. And there's our answer. Well, we got one more thing, class. Remember, in standard form, we put the variable terms first from highest exponent to lowest exponent. Well, the imaginary part of our answer is always going to go on the end. Okay, so that means we're going to rewrite this to be 15 plus 3i. And let's make a little notation here. The imaginary part, the imaginary term, always last. Always last. Okay, so that's how to add and subtract complex numbers. Pretty easy. It's exactly the same strategy as adding and subtracting polynomials. Alright, how about multiplying complex numbers? Multiplying complex numbers. Let's go ahead and put an example up here. Let's say we want to multiply 6 minus 5i, and we're going to multiply that times 3 plus 2i. Again, the good news is your strategy is exactly the same as when you're multiplying two regular binomials that are not complex numbers. Let's go ahead and follow our procedure. We take the first binomial, we split it apart, and we're going to multiply it by the second binomial. Here's the second part of our first binomial, and that's going to get multiplied by the second binomial. So you can see we have split the first binomial into two parts. Now we're going to go ahead and do monomial times binomial. 6 times 3 is 18. 6 times 2i is positive 12i. Negative 5i times 3 is negative 15i. And negative 5i times 2i, now let's do the same thing we would do with the variable. Negative 5 times 2 is negative 10, and I times I is I squared, just like it would have been x squared. Okay, let's remember something from our previous part of our video. I squared is just negative 1. So let's go ahead and combine our like terms in the middle, just like we would normally. So our next step, we're going to have 18. Positive 12 minus 15 is negative 3, so negative 3i. But now we've got this whole interesting thing happening. I squared is actually just negative 1. So we can actually multiply those together. We've got 18 minus 3i. Negative 10 times negative 1 is positive 10. And now we've got one more set of common or like terms that we can put together. So 18 plus 10 is 28. And our final complex number as our answer is 28. And then we've got a minus 3i. So this looks exactly the same as multiplying two binomials. The only thing is that when you get I squared, you can change that to negative 1, and then you can do a little bit more simplification. And I'm going to, on our previous part, let's go back to this part. Let's go ahead and at least circle our final answers. Okay, so last part of this video. Let's see how this works when we're using the quadratic formula. So it says, using the quadratic formula, what are the solutions of x squared minus 2x plus 7 equals 0? Well, let's go through all of our steps of using the quadratic formula and see how this works out. So the first thing we look at is, what is a, b, and c? So a is 1, b is negative 2, C is positive 7. Remember, class, you don't have to pull any GCFs out when you use the quadratic formula, but you do have to have all of the terms on one side of the equal sign. The equation has to be equal to 0 because we are trying to find the x-intercepts. That means that y has to be 0. So we're treating the right side here as our y value. Okay, step number 2, after finding a, b, and c, let's find the discriminant, and I'm going to write it out so you guys can see that I'm following the procedure in our flipbook. Our discriminant is b squared minus 4ac. b is negative 2, so we've got negative 2 squared minus 4 times 1 times 7. Negative 2 squared is positive 4. Remember, you square a number, it's always positive. And then 4 times 1 times 7 is 28. This is 4 minus 28. You can do that in your calculator if you need to. And 4 minus 28 is negative 24. So our discriminant is negative 24. Next thing we do is we're going to find the x-intercepts. X-intercepts. So now we're going to plug this into our entire quadratic formula, only now we already know the discriminant. So we're going to have negative b plus or minus the square root of our discriminant, which is negative 24, over 2 times a. Let's go ahead and plug in our b value. b is negative 2, so negative of negative 2 is positive 2 plus or minus the square root of negative 24 over 2 times a? Well, a is 1, so 2 times 1 is just 2. So we have found our x-intercepts. Let's put a box around that. I'll slide that down a little bit if I can. See if I can actually do that. There we go. So we found our x-intercepts. Okay, in the next step, we talked about if we can simplify the discriminant part of the equation, we're going to do that. So we're going to put on here simplify the square root, if possible. Well, our square root is square root of negative 24. We can simplify that because now we have this thing called an imaginary number. The square root of 24 actually can be written as, actually I'll put an arrow here so you guys see. This could be written as the square root of negative 1 times 24. We agree that negative 1 times 24 is negative 24, so nothing's changed. Now we can also write that as the square root of negative 1 times the square root of 24. Class, we talked about this probably. If you've got two numbers multiplied together that are inside a radical, you can split them up as separate square roots. And now here's this imaginary number showing up. The square root of negative 1 is actually I. So we can rewrite this as I times the square root of 24. And since the square root of 24 is not a perfect square, we're done with simplifying our radical. And now we're down to the final answer. So our last step is our final answer. And we can write this as x is equal to, and I'm going to write this just as one term here instead of splitting the terms. We can just do it as one term. We've got, here's our x-intercepts. We're going to write 2 plus or minus. Now we're going to put our simplified square root. We've identified the imaginary part, I times the square root of 24, and that's all over 2. Now you know sometimes I've written this as 2 plus I times the square root of 24 over 2, comma, 2 minus I times the square root of 24 over 2. In this case, I'm going to save some writing and just write both of them together as one. This plus or minus sign means we can add this to one of our x-intercepts, we can subtract this from one of our x-intercepts. And there's how we use the quadratic formula and deal with a square root or a discriminant that happens to end up being negative. We can pull out the square root of negative 1, change it to I, write our final solution. And class, one more thing you'll notice about this is if you graph this parabola, you will see that this parabola does not cross the x-axis, and that means technically we have no real solutions. We used to just talk about it as there are no x-intercepts or no solutions. Now we're going to say there are no real solutions, but there are imaginary solutions in math, but there are no real solutions.